Hello, everyone. Good morning. Thank you very much for your interest, and thank you to Steve Nolan for this presentation. This is titled Reinventing the Wheel, Stronger, Lighter, Faster, UHPC Structural Design. Steve has been a registered PE in Florida since 2001. He received his engineering degree from the University of New South Wales, Sydney in 1989. Then he worked as a construction engineer for a heavy civil contractor before moving to the US in 1996 and joining FDOT. He currently leads the implementation of novel structural materials for bridge applications within the FDOT State Structures Design Office. These materials include UHPC, FRC, various FRP composites, and Steve coordinates this as chair of the statewide Structural Advanced Materials Technical Advisory Group. He has 27 years experience with FDOT, and this includes in-house bridge design analysis and detailing, standards and specification development, design policy refinement, and technical training development delivery. Thank you very much, Steve, and this is all yours.
Well, thank you, Prannoy. Well, good morning for those in Florida, at least. My name is Steve Nolan, and I've been in Florida for 27 years. Professionally working at the Florida Department of Transportation, but as Prannoy said in the introduction, I came from Australia originally. So you had a copy of my bio that was distributed in the flyer, but I just highlighted some of the points within there that's really the real Steve. And so a lot of my influences through my university education and early career are splattered around the screen there. I was born in the middle of the building of the Sydney Opera House, which is was a pretty innovative structural design at the time. I have spent many years around the Sydney Harbour Bridge, actually even climbed it when we were in college. And so bridges were always something of interest to me. And luckily I found some way to engage in that passion later on. But right out of college, I started working for a large civil contractor, and that photo on the bottom is the first dam we constructed. Had a lot of toys, Tonka toys on that project, large heavy earth moving equipment. And my jobs were dealing with the concrete and steel. And so we had one engineer doing that and about 5 doing all the other activities that made the most money. But that was a very enjoyable experience, and I worked on several other projects, got to work on a bridge eventually before I left and went out to see the world. It's when I met my wife in Europe in 1993. You see her in the bottom right, and thought I'd hang around for a while. And 2 years later, a year later, we decided to get married. And 2 years later, after that, I moved to the US. And so was that the right decision or the wrong decision? Definitely the right decision for me, but that's a circuitous path that brought me here. And many of you, I'm sure, have similar stories. So what are we going to talk about today as far as reinventing? I had the wheel, but I struck that out because we're not really building wheels here. But it is using some knowledge that we've gained in the past and leveraging that to perhaps accelerate the development and deployment of these structural technologies in the future. And so we're neck deep in the middle of ultra high performance right now at the Department of Transportation, trying to figure out where it best fits and what to do with it. And as part of that, and actually part of some of my earlier career work at DOT, I researched pretty heavily the beginning of the pre-stressed concrete industry in Florida, and it's pretty impressive what was done here and how quickly it proliferated throughout both the building and transportation sectors. And so there's some nuggets of knowledge there, I think, that can be captured and lessons learned from that, and perhaps moving forward, just understanding why that was so successful, and also seeing some of the problems and challenges and how they overcome those. We obviously don't have time to get into all of that today, but I will lead you to some resources if you want to follow up later that have some pretty interesting reading, at least if you're an engineer. I'm not sure my wife would agree, but that's okay. So we'll talk a little bit more technically about, what's driving the innovation, what's driving the need for a change in materials, what's seems to be the key parameters that make it successful. This push and pull factors is used in a number of industries. There's actually a bunch of engineering papers out there talk about what are the motivations forcing a technology into the system, our society, and what are the forces pulling or seeking solutions to existing problems and challenges. So that's what the term push and pull is going to be used in the context of this discussion. And then we can look at how these other historical lessons can be used to maybe make our lives easier, maybe do some exciting work, maybe make society a little bit better at the end of the day. So just a brief outline. Dig pretty deep into pre-stressed concrete in Florida, specifically related to transportation. I mean, there's a lot that went on in the building industry as well, vertical construction, and that's well documented by PCI as well. So you can follow up on that. Little explanation about what's great about UHPC, or what we think is great about it, and what are the real needs that we have, or owners have, that this would be a great solution potentially to solve some of those, and how do we apply the lessons of the past to moving forward. And then we'll go into some of the recent uses and current things that we're looking at, opportunities as we move forward. So, as all good engineering presentations have charts and equations, I don't have any equations today, but certainly plenty out there that we can offer. So what are the advantages first of pre-stressing? You probably all know this, but in specific context of bridges, it allows us to have longer spans, obviously, which really means we get to have fewer foundations, and there's a lot of cost in the foundation construction. And so it's also a very relatively slow process. Pile driving, drill shafts, we typically don't do caissons or footings anymore, at least in large bridges. And so it's not just the greater electrical capacity of the beams. There's real cost savings there in production as well for the contractor. The pre-stressing concrete allows us to get away with more slender elements than inner elements. We're using less material, so therefore it actually is more sustainable. It reduces the weight of these elements, so therefore the handling costs for the contractor are less. And so when you precast, you can accelerate construction because you're doing all those activities concurrently with what you're doing potentially at the site. And so it's faster erection. There's actually faster fabrication when you pre-stress as well, because we're able to turn our forms over usually in 24 hours. Whereas if you just did mild reinforced concrete, at least if you're casting beams, bridge beams or something, or piles even, you need to wait a few days to get that concrete strength before you pull it out of the form, and to avoid cracking and other damage. So Durability, in many cases, you have a better structure in service from a durability perspective, because you can have it uncracked during service. Reinforced concrete, as we all know, has to crack to really engage the reinforcing steel, but pre-stress does not. And so, so that's a major benefit for both piling and bridge girders. And then aesthetics, that's subjective a little bit, but more slender looking structures generally leads to better aesthetic perception from designers and the public generally. So just looking at the pile interaction chart here, I have in the blue lines our current pre-stressed square concrete piles. I think this is a 30-inch square pile, which is pretty common on our large structures. And so typically the piles are operating in the range of the bottom third of the compressive part of this chart. And so we don't really get to use the full flexural capacity under combined axial and bending, just because there just isn't that much load being added to the bridge for the strengths of the concrete that we typically use, which is 6,000 to 8,000 psi concrete. So the dashed lines are just the nominal capacity, and the solid lines are the resistance factored or V factored strength reduction factor, depending on what code you're designing with. And so that's what we're allowed to utilize in design under our factored loads strength limit state. So when we use UHPC, and we'll get into that a little bit later, we get a significant more capacity because we can utilize that compressive strength when we have a pre-stressed concrete member. And we're all pretty familiar with the advantage of pre-stress in general. It allows our service to be in uncracked condition. And so we get slightly higher flexural capacity at ultimate, but that really depends on the configuration. So, sure, I've got a clock on my time here. So going into the Wayback Machine, we've got some pretty significant structures historically in Florida that were built. And I don't know how familiar you all are with pre-stressed concrete history, but it had started in Europe in the 20s with Eugene Frechnet, and there was also some work in Germany. And there was also this professor, which I hadn't heard of in college, maybe you all, from Belgium, Gustav Mandiel. And he was the one that really was instrumental in bringing pre-stressed technology to the US. The first bridge that was constructed was the Walnut Lane Memorial Bridge up in Pennsylvania, Philadelphia. And that was like 150-foot span, which was very aggressive, very ambitious, let's say, compared to what can currently be designed and constructed in Europe. And there's some rather amusing comments in one of the PCI journals about how contractor made the observation that the first bridge that the Americans built is like the longest one that the Europeans took 20 years to get to. So we sort of shoot for the stars here on the first round. And I mean, and it was successful. There were ultimately some durability issues that caused the bridge to be taken down in it was the late 80s. But yeah, it stood pretty significantly as a monument to the effectiveness of pre-stress concrete very early on. In 1949 was when that project was let. A couple of years previous to that, Florida had tried to execute a project across Tampa Bay, so now known as the Sunshine Skyway. And the cost came in far exceeding the available budget, and so they had to go back to the drawing board. And so as they were working on a redesign, Gustav Manuel and his former student, Charles Zollman, from the US, approached the then state bridge engineer or chief bridge engineer, Bill Dean, about considering pre-stressed concrete. And Bill had obviously had a little experience with pre-stressed concrete. A few years previous, and I don't know what the circumstances were, but he wasn't too thrilled about it. But back then, before the internet and everything else, there wasn't as free a flow of information as quickly, and so they apprised him of the success on the Walnut Lane Bridge design, and it hadn't actually been constructed. Didn't get constructed until I think 1950 was the start date. 51 was a completion date. So all these things were happening concurrently, and the Florida Department of Transportation, which at the time was called the State Road Department, entertained an option to use pre-stressed concrete as an alternate to reinforced concrete beams on these Skyway bridge approaches. Not this main span that you see here; it's a steel truss. But all the approaches you'll see in the next slide are a significant portion of the contract. It's by far the greatest portion, cost of the contract. So if you're not familiar where this is, Tampa, there's a big red star there in the 1950s map of Florida. So, so this was a 21-mile stretch of roadway, I think it was, but there was more than 3 miles of bridge, which was a pretty huge feat back in the 40s, really, was when it started. And so they designed, after the failed bidding attempt in 1946, 2 options: one, reinforced concrete T-beams, basically what they were, precast T-beams, or cast in place. That was sort of up to the contractor. Or the other option was pre-stress, and that was obviously going to be precast. And the advantage was that they could get 1/3 longer spans with the pre-stressed concrete. So they were able to reduce the number of foundations and also speed up the construction, which led to a lot of savings for the contractor. So with the bids coming in, the pre-stress option was selected, and they got in under budget this time around, and so they began building this really ambitious project, and was successfully completing that by 1954. So there's a picture there on the bottom left of Chief Bridge Engineer. Several years after this was 1964, when he was inspecting the Sebastian Inlet Bridge, which is another significant structure that we won't go into today. But Bill also was instrumental in establishing pre-stressed beam standards for the US with the UHPC Joint Committee. He chaired that committee, and so he was engaged up until his death in 1965. On the right there is a picture of Eugene Fresnel. Everyone should know who that is. But his influence on all the earlier players is significant also. So then, after the success of that project, the Precast Concrete Institute was formed in around 1955, I think. And so they had a course that was developed to educate engineers, because obviously there was really not anything at the time in formal training in college. And so this photo is 55, the guy on the left is Charles Zolman, who was Manuel's student, and Bill Dean on the right. The most flattering facial expression at that time, but that's okay. But I encourage you to go to this publication on the right, the reflections of the first 25 years of pre-stressed concrete in America, really North America. And there's a short extract in there, a short paper from Bill Dean on the outlook to the future of pre-stressed concrete. And it's pretty insightful. The guys were did a lot with limited tools at the time. And I'll talk a little bit about that in the next slide, but there's a link at the bottom of the screen there, or you just Google 25-year reflections PCI, and there's a vast array of knowledge in that document that was assembled over a couple of years by PCI and published in their journal. Most of the articles are pretty easy to read too, they're not that technical. But I like the introduction to this article that Bill Dean wrote. It's like, the title of this paper would indicate a clairvoyant ability on my part for which I make no claim. In some 25 years of engineering practice, I've had little experience with the use of crystal balls, tea leaves, or zodiacal signs. And it goes on, but that's just an indication of his skepticism, I guess, about predicting, innovation advancements and whatnot. So he was a very practical gentleman, and there's an interesting history there, helping promotion of pre-stressed concrete and bridge engineering in general in the 50s and 60s. So then we skip to the 80s. There's a lot that happened in between there, but Sunshine Skyway was unfortunately hit by the Summit Venture, and one of the spans collapsed with multiple deaths, and so the state had to demolish and rebuild that bridge, and they chose to demolish it, build it taller and stronger, and that was again a pre-stressed concrete, and this time it was post-tension segmental on the main spans. The approach spans were still pre-tension concrete, and so that 3-mile bridge was rebuilt in with the main span being cable stay, and that was really the idea of Jean Mueller, who was a French engineer, and he had been a student of, not so much a student, but he had worked for Eugene Fresnel in France, and so it's a pretty small world when you get into it. A lot of these people are all connected, but Jean Mueller had designed the Breton Bridge in 1977 in France, and they showed that to the governor of Florida at the time, and he was pretty impressed, and so that option was advanced. I mean, I think there was 3 different options for the approach spans, and then the main span was really selected to be cable stay. I was given a copy of some of the hand calculations that John Mueller had performed in the initial design of the structure, and they're pretty artistic and they're pretty impressive. I mean, in that one on the screen right there, he's looking at the thermal effects of the shadows of superstructure on the tall column there, and so looking at the different arcs of the sun and the shade effects both in summer and winter, and so they were really looking into that pretty deeply with very limited computing power available to them at the time. Earlier, they had started segmental bridge construction, non-cable stay in Florida and the Florida Keys, and so some of the first segmental bridges were precast segmental bridges, not cantilever, that had been started earlier. Cast in place cantilever, which still used quite a lot in California due to seismic reasons. And so, yeah, Long Key, I think, was the first, and then Niles Channel, 7 Mile Bridge, and a few others that basically was the real foundation for post-tension precast segmental concrete in Florida. We've had some challenges in recent years, but you have to remember that all these bridges were designed for a 50-year design life, and so most of the structures that we have well exceed that. I mean, in average, our bridges are 60 years old by the time we replace them. So for the expectations at the time, they do pretty well. But clearly, Florida is an aggressive environment for corrosion, and so there's been some challenges with maintaining the structures in there. Not pristine, but sufficiently working condition. So going back to something a little more simplistic, double T's. This just shows the progression of development of double T's and some of the thought processes that go through and evolution of some of these structures. And so the double T beams are used still extensively for parking garages and some building works, but it had an interesting development history, and the reasons why they settled on the double T version are interesting in themselves. And so you have just towards the end there, you have the single T developed by T.Y. Lin. And although it was very efficient, from a constructability standpoint, it was challenging because they weren't self-supporting for storage and transportation. So that's where the double T really came in to be an ideal element. And as crane power or crane capacity increased, so could some of these options. Back in the 40s, an 8-foot wide double T probably wouldn't have been practical for the spans that you needed. So as construction technology improves, and so can our designs and the options begin to expand. So moving on to the mid 80s and early 90s, pre-stressed concrete beams really proliferated in Florida and the rest of the US, but we started making them continuous using splice girders because we have these intercoastal waterways that require pretty wide openings, and typically we struggle to get above 150 feet with a simple span, which isn't always enough for these coastal waterways. So here we have a picture of some full-scale testing that was done prior to the construction. It was part of the construction project, but galley beam tests were done in 1985 with the splice girder technology, which was almost brand new at the time. And over that short period of time, Florida had built 12 of these splice girder structures, and then 5 more major bridges with bolt T's. You can see scattered around the coast there, and see where they all are. They're all along the coastline, and they're all really intercoastal waterway crossings. So that was the need. That was the pull for this type of construction. I will say it's relatively tedious, slow, relatively speaking, and so that's one of the challenges and one of the motivations we're looking at moving forward with UHPC, because to get a 250-foot span, which is 250, 260, which is typically what we would target with these types of designs, there are some advantages to that. Avoid fender system, you reduce the ship loading impact on the foundations, and so there's a cascade of effects. And So the holy grail at the moment is to do a 250-foot simple span UHPC girder. We're not quite there, we don't think. And cost-wise, I think we're a ways away from it. But that could change pretty rapidly. So after 50 plus years of the original AASHTO shapes that proliferated around the US, our demand for longer spans really necessitated us being Florida Department of Transportation, looking at a more efficient and girder that could span much further. We're looking to routinely go in that 150 to up to potentially 200-foot range. And so to do that, we needed more pre-stress in the bottom flange. We were limited with the current designs. And so we came up with a shape which eventually became known as the Florida I-beam, or FIB, as we call it. And so that work started, really initiated by Sam Palaha and Robert Robertson. They work closely with the Florida Precast Concrete Association, and it went relatively quickly, the development. I mean, we were just reusing existing technology and practices, but there's a huge expense in setting up these forms, and so we had to get buy-in from the precast industry, and we had that conversation with them several times and got their input on what shapes were practical. And luckily, we were at a juncture where a lot of the precasters were looking at purchasing new formwork, and so that's a huge expense for them, capital expenditure that they amortize over time. And so by having these conversations, we were able to get their buy-in, and they avoided some unnecessary expenses of buying existing formwork and just waiting with their older formwork until they could gear up for FIB production. So we started out with a vision of having the same shape in the bottom of the beam, or really the same shape beam, just extending the web, which works practically up to a point. It's a little inefficient for the smaller beams, and as we get to 8 feet, we begin to need perhaps a wider web. Now that was prior to the consideration of UHPC, and so the rules of the game changed a little bit with that. But 2009, we rolled out the standards. They actually had constructed the beam prior to us even issuing them. It was a design build project, and the design build contractor wanted to utilize the shape in lieu of the existing bold T shapes that we had for obvious advantages. And so the state Department of Transportation allowed that. And then over the next few years, there was a rapid succession of projects, even outside of Florida. I believe the first project was actually in South Carolina that used our standards as a design build. So obviously there was something right there that we'd done. And so 2012, the Big John Monahan Bridge, 185-foot span. That was a 7-foot deep beam. And then the longest one in Florida to date was the 436 interchange with a 96-inch beam, so 8 feet tall. That's a monster, 209 feet. So that was 2005. And that was, again, a design build project. So we weren't forcing this on the contractors. They were volunteering to take this on. You need huge lifting equipment and transportation to be able to manage these girders. And so it's one of the advantages of the design build process. You get to find out what contractors really really want. I mean, ultimately it's saving money, but what's practical with the equipment they have and what's feasible moving forward. So that was pretty impressive. That still is pretty impressive. We still don't see too many 209-foot spans because just it's very expensive to transport it that way. But in this case, it was it fit the needs of the project. I will say that Washington State DOT is beat us hands down. They've done a 223, I think actually they might have been a 230-foot girder now. We call it a WG, a wide top flange girder with 105 inches. So whatever that is, that's like 8.5, 8+ feet. So you got to keep making these things deeper because you do end up with some stability challenges with handling these girders that long. And so the top flanges, as we look at maybe before we consider UHPC, if we were to go to the next level, go above 209 feet, we would have to probably consider widening the top flange from what is currently 4 foot wide to 5 for stability handling purposes. That actually hurts you structurally for the span length, but yeah, those are some of the trade-offs you have to make. It's like this drawing here. If you go back and look at the old ASHTO beams that were distributed by PCI and ASHTO, they did a original drawing pretty much the same as, well, they did it first. We copied out it and did the Florida I-beam in the same style, except for the isometric 3D rendering. So, and all the team got to sign the poster, and it's hanging in our office up in Tallahassee. So that's pretty neat. Just discussing the development process, we had envisioned a 10-foot beam when we first started looking at it, but that obviously hasn't come to fruition yet. But we did decide on having some intermediate sizes to basically correlate well with our existing structures, existing forms. So we'll transition now into ultra high performance concrete. Quickly, I don't have too many slides here, but this is sort of the new shiny toy on the block. It's not that new, really. It's been used in France and in Europe for more than 20 years. Actually, no, they built a bridge, a high-girder bridge in Australia in about 2002 or 4, I think it was. So 20 years ago. I think it's the only one they ever built. It's just the cost is just hard to justify, or was hard to justify at the time. It's becoming more reasonable as far as a cost-effective solution, but you have to find the right combination for that to really work. But the attractions are that it's essentially 3 times stronger than high-performance concrete, has twice the modulus of rupture generally, but the most important thing is the post-cracking ductility, so you get this strain hardening effect, or at least strain leveling, which I should have put a chart in here, but next time perhaps. And then durability wise, a lot of the testing indicates that it's almost impermeable to chloride diffusion, which is good to avoid corrosion. But we're not really sure how that performance goes when it's cracked under service conditions. So we've got some research looking into that aspect. And that sort of drives the concrete cover that we need, which then drives the thickness of the section. And so all these elements are interrelated, and thickness of the section drives the weight. And so you can see that it takes a smart combination of all the parts to make it really effective. It's expensive. I mean, the materials are, in relative terms, You know, a cubic yard of concrete is maybe $130, $180. Might be a little bit more these days. A cubic yard of UHPC is in the order of $1,500, maybe $2,000. It really depends on the fibers. It's a significant cost share of the material. But then there's a whole bunch of handling issues, or costs, let's say, storage, different materials. And so in the end, we're paying significantly more, at least for the on-site applications where we have to even mix it on site. So you have all these logistical challenges to the costume as well. So we got 3 minutes left, I think, Pranay, so I might make it. The chart on the right here is was shared with us earlier this year by JP Bernard, who's been heavily involved in the UHPC precast industry. It's a pretty accurate reflection, I think, of the development process that we've gone through in the US. We're getting UHPC technology implemented. We're still working on specifications. We have guide specifications going to vote for AASHTO. ACI is working on structural design guide document. It's still several years out. And so codification is the ultimate goal, but we're a little way away from that at this point. So what's Florida DOT done is with the use of UHPC, apart from connections, we use it a lot for connections, but for precast, we started looking at piles. Well, we actually didn't. The precasters came to us and they just made these piles and said, here, this is what we can do. Why don't you test it in your structures lab? And so we did a little bit of that. We've even driven some of these piles. We have contractors have. There's a real interest from the precast industry to move this material forward. We're still trying to find the right balance. We looked at this pile interaction chart earlier, and so we talked a little bit about under high compressive loads, you get significantly more flexural capacity. So how do you get that compression? Well, you can get it by putting more pre-stress into your member initially. This whole red curve shifts down there. And so that's what we're looking at now, typically. How much pre-stress can we pack into this to really benefit from the structural performance of the material? And there are some geometric limitations with the size of our beams, the size of our piles, the spacing of the strand, the size of the strands even. So there are 0.6 strand is the largest standard strand. We use 0.6-inch diameter. There are 0.7-inch diameter strands out there that are standardized by ASTM, but there's a reluctance from the precast industry to use them just because they're much heavier to handle and more dangerous if they do have a problem. And so there's always this balance that you've got to try and achieve to move forward. So our top right is just one of our typical applications for rehab of sonovoid bridges by hydrodemolition of the joint connections and then casting back UHPC, which I like to think of as basically welding these structures together because you get really good connections if you construct it right. So the advantages, again, for UHPC are going to be similar to what pre-stressed concrete were. You're going to be able to get even longer spans, so even fewer foundation units. Foundation units have to go up in capacity a little bit, but still there's a net benefit. Even thinner sections, you've got to be careful about stability and buckling even. At some point we're going to get into the zone of where buckling for concrete is going to be a concern. So faster fabrication, we're not real sure about that. Durability, we think so, but there's still some questions on cracked UHPC. Aesthetics, again, more slender structures are generally going to be perceived as better. And then, so just the last few slides are just some of the options of structural elements that we've looked at. So sheet piles, we started with the top right shape, and we had a consultant look at a little more sophisticated connection. In the end, we didn't really love that. We're still struggling with with how to do the sheet piles most effectively with UHPC, because you have to save a lot of material over our just rectangular section that we typically use, which is pretty easy to build and install. It's just heavy and inefficient. One option we're looking at in Prannoy is like hexagonal or octagonal piles. And I think there's some potential there. It's nothing, we're just exploratory at this point. That would look familiar. It's sort of like the sea hive shape. So the octagonal pile, which is used on the West Coast, has challenges with the void floating, and so there's some constructability issues. You're not sure what you get, the potential for corrosion inside that can't be inspected. And so we're like working through those benefits, pros and cons against potentially other shapes. And so we've sort of settled on the H shape at the moment for several reasons. And so that's the one we're pursuing with the precast industry, and we've been keeping them in the loop. And so this H shape that was originally prototype developed and driven in Northwest Florida is going to be refined into a standard in the next few months. And so it'll be the first step, and no doubt we'll improve on that over time. The voided shapes have an advantage for stability and scour, less scour issues in waterways. So we'll see. We'll keep looking at that. For bridge girders, the consultant we had looking at sheet piles also looked at what we could do. How could we get to 250-foot spans? And the one on the right is 108. So that's was that 11 foot? Sorry, no. 9. My math isn't that good, growing up metric, I guess. So that's a 9-foot girder, which is pretty tall. But you can see it, the slenderness of it is a lot different than our current shape. So 4.5-inch web, we're pretty confident that that's not going to be too much of a challenge for us for shear and stability. We'll see. We haven't decided on standardizing this yet, but it's that conceivably on paper can get us beyond our 250-foot span if needed. So we've also looked at using UHPC in the ends of our conventional beams to be able to get more pre-stress in without cracking, or even improve the shear performance at the end. We've looked at box beams, voided box beams for our existing shapes. So we're throwing a lot of stuff against the wall, and we'll see where we land and what sticks in the next couple of years. So so with that, that's all I have to share today. And any time for questions?
Thank you, Steve. I'm sure we're going to have a question from the audience.